Okay, so I'll be doing a workshop on Shinigami. I'll start with kind of explaining what it is, and then I'll go into the basics of like what script is, and then see where we go from there. So Shinigami is pretty much a start client for Bitcoin, or it's a set of start tools to be used for scaling Bitcoin in different ways. So essentially, the Starkware team's kind of goal in general with Shinigami and exploration projects that we're working on is scaling Bitcoin with and without soft forks, figuring out all the different ways that we can use Starks to help Bitcoin reach mass scale. So that's where Shinigami comes into play. So Shinigami is a set of libraries written in Cairo to allow us to use the power of Starks to superpower Bitcoin. And since we're using Cairo, it allows us to be natively provable, and I'll kind of go into what that means in a bit. But Shinigami is kind of split into two different parts. There's the execution and consensus libraries. The consensus library can also be referred to as Rhino, so y'all might hear that name floating around. But I will be mainly focusing on the execution part because that's what I've worked on, but I'll go into the consensus part as well. So Shinigami execution. So what Shinigami execution library is it's a Bitcoin execution engine written in Cairo. So essentially what that would mean is that we want to execute Bitcoin script in a way that we can create start proofs of that execution, which would allow us to run super fast. So if you're not familiar with Bitcoin script, I'll kind of go into some basic examples. So a lot of people aren't familiar with the fact that Bitcoin actually does have a scripting language. It's basically just like an assembly language that has a handful of opcodes, I think around like 150, depending on how you count them. And this is a very, very basic example where we're just adding some numbers together and comparing that they're equal. So we start with op2, which will push 2 onto the stack. So Bitcoin script is a stack-based language, so every opcode interacts with the stack. So op2 will push 2 onto the stack, op3 will push 3, and then op-add will take those two numbers off the stack, add them together, and then put the results back onto the stack. So we end up with 5. Op5 will push 5 onto the stack, and then op-equal checks that the two values on the stack are equal, and if they are, it'll push a 1 onto the stack. Since 5 is equal to 5, we get 1. And at the end of a Bitcoin script execution, we check the stack, and if at the top of the stack it is a 0, then the script is invalid, and otherwise it is spendable. And since 5 was equal to 5, we know that this transaction would be spendable. Not a super useful script because anybody could probably figure out that 5 equals 5 and then spend your Bitcoin. So let's kind of go into a more realistic example of how Bitcoin transaction execution will work. So how the Bitcoin state is laid out, essentially there's a bunch of UTXOs. It means unspent transaction outputs. So these are all different Bitcoins that people own, and they're nested in these UTXOs. So let's say you want to spend UTXO 6, which has like 3 Bitcoin in it. So there will be some locking script associated with the UTXO. I'll be doing a very simple, it's probably the most simple kind of locking script that's on Bitcoin mainnet now, is a pay to public key. It essentially consists of 2 opcodes. So the first is an opcode that pushes the owner's public key onto the stack. So if you own UTXO6 and you want to be able to spend it, then you should have the private key that links to this public key in the locking script. And then the last opcode is op-checksig, and we'll go into that. And let's say you want to spend this UTXO6, so you'll pass this transaction or you'll send this transaction to the Bitcoin network, which consists of the inputs and the outputs. So the input would be UTXO6, a reference to the UTXO that's in the Bitcoin state. An unlocking script, you'll give the unlocking script, which is a separate Bitcoin script from the locking script that's in the UTXO that is used to unlock the Bitcoin. And you'll give a new set of outputs, which will be a new set of UTXOs that you want to put into the state. Say, if it's another pay to public key, you'll have another UTXO with somebody else's public key in there so they can spend the Bitcoin whenever they're ready. So let's kind of go into the flow of how this transaction executes through the Bitcoin engine and also the Shinigami engine. So we start with the unlocking script, first executes. The unlocking script for a simple pay to public key is just the signed transaction data. So it'll just push the signed transaction data to the stack, and then it's done. It's done with the unlocking script. And then UTXO6 will execute. We kind of went over what the script was there. So first, it pushes the owner's public key onto the stack, and then opcheck sig executes, which is a pretty complicated opcode, but I'll make it a little bit easier, hopefully. So essentially what opcheck sig does is it takes the signed transaction and owner's public key off the stack. It checks that this public key can, in fact, decode this transaction, meaning that the owner signed the transaction properly with their private key that's linked to this public key. And if it was, in fact, a valid signature, then we say, hey, we push 1 onto the stack. If it wasn't a valid signature, we would push a 0. And like I said at the beginning, since there's a 1 on the stack at the end of the script execution, we know that this transaction is valid. So this new UTXO can go into the state, and the old UTXO6 will be removed from the state because it was spent. And this new UTXO will be linked to whoever you sent the money to. Bitcoin has like the ability to have arbitrarily large, or not arbitrarily large, but very large transactions with a bunch of different inputs and a bunch of different outputs. This simple example that I went through is just 1 input, 1 output. But you could imagine having like 100 different inputs, and each input you'll pass an unlocking script in your transaction and provide as many outputs as you want depending on who you're sending the money to, or if you want to send certain parts of the money back to yourself and so on. I put a couple examples of some large transactions on the Bitcoin network. I think one of the largest transactions at the beginning of the Bitcoin's lifetime was the infamous or famous, I guess, 10,000 Bitcoin pizza, where somebody spent 10,000 Bitcoins to buy a pizza on the mainnet. It had like 130 inputs, so it was a relatively large transaction. You can imagine more complex computational transactions like a 20 of 20 multisig, where you need 20 people to sign the transaction and pass their data or pass their signatures to the transaction to be able to spend. And a recent development that's, I imagine, will be a super large script if it's ever implemented on mainnet is something called Collider script, which is essentially a script that will allow people to do covenants, or it seems like it would allow people to do covenants on Bitcoin today, but it requires like a SHA-1 and a RIP-EMD implementation in script. So if you were to implement those in script, the transaction will be massive when you're spending. So yeah, I also put the limit for Bitcoin transactions on mainnet. The theoretical limit for a transaction size is about 4 megabytes. So each opcode that executes is about 1 byte, or it is 1 byte, but if you do like push data opcodes, you can have more. So you could have like 4 megabytes worth of opcodes in any transaction, and all of those would need to execute one after another. So it could be pretty computationally intensive. So that's where Shinigami comes in. I'll kind of briefly discuss Cairo here. So Cairo is a Rust-like Turing-complete programming language developed by the Starkware team. It allows you to easily create provable programs in like a normal programming way, like instead of having to build like custom circuits or do anything crazy like that, you just program like you normally would, and by the nature of building in Cairo, you're able to execute those programs in a provable context. And Cairo's been used a lot for StarkNet and things like StarkX exchanges, so it seems to be pretty battle tested at the current state. So those are some pros of using Cairo, which is why we built the Shinigami engine in Cairo, which will allow us to compress we can compress a lot more transactions than the 4 megabyte limit into a 4 megabyte proof to post onto Bitcoin or any other chain that we want to prove the transactions on. So now I'll kind of go into the coding section, or like go over the code of the Shinigami engine. So this is a bit of a reduced version of how the Shinigami engine works. It makes it easier to fit on a slide and easier to look at. So essentially, when we want to execute the transaction, we first loop over each of the scripts. Like I discussed, those are like the unlocking script and the locking script. And if you have like witness or anything like that, or newer Bitcoin types of transactions, you execute those as well and you loop through them. And then for each script, you just loop over all the opcodes. all the different types of opcodes like push data, manipulating data, doing hashes, signature checks, and things like that. And then for each opcode, we execute it through the Cairo program. And then at the very end of the script executions, we check if it's valid, if there's like a 0 or a 1 at the top of the stack. And if it is, we know that it's a valid transaction. So like I mentioned, each transaction can have multiple different types of inputs or multiple different inputs. So this is the function that we use in the Shinigami engine to validate transactions. So we loop through each of the inputs or the UTXOs to spend. We create an engine instance with the transactions data and the public key or like the unlocking script, and we execute the script and check the results. And if there was no errors, we know that the transaction was spendable, so it is a valid transaction. Otherwise, we return an error, and the caller can indicate that to the proof that it is not a valid transaction. So I will go through a basic example transaction through the Shinigami engine. Here, this is the very first ever transaction from Satoshi to Helfini. I'll kind of explain it a bit. I want to look at the details. So this is the transactional mempool.space. It's like one of the famous Bitcoin block explorers. But essentially, this is the transaction here. So you can see the script sig, which is what I called the unlocking script. Yeah. So the script sig is the unlocking script that is passed with the UTXO. So you can see here that it pushes, it is passed by the transaction. We can see it's just one simple opcode that pushes the signed transaction data to the stack. And then the previous output script, this is from the UTXO. We can see it just does one push data opcode that pushes the public key. So this is the public key from the spender. You can see here that it's the same as the public key that was sent to, and we do the op check sig. So it's a very simple pay to public key transaction. And here is the same transaction on something called Learn Me Bitcoin. I just wanted to show this one thing. Essentially, this is the transaction data. So all of this is just like a bunch of numbers. You can't really read it, but if you were to like look at individual parts, you can see that this is the input that the user provides from the UTXO. So this is like a reference to the UTXO and state here based on the transaction ID and like which output it was. And then this is the unlocking script that the user passes with their transaction. And it is all stored like in this raw transaction data that the user passes to the Bitcoin network. And then at the end, we have like the outputs that we want to pass to the new Bitcoin state so people can spend the transaction in the future, or spend the UTXO in the future, I should say. Okay. So what I just showed on Learn Me Bitcoin is like all this raw transaction data. And what we do first in the Shinigami engine, or like to test the Shinigami engine, is we deserialize that data into a transaction type, which consists of like the inputs, the unlocking scripts, and the outputs. We set up the Bitcoin state, or the assumed Bitcoin state here with just the locking script in the UTXOs. And there's only one UTXO being spent here, so we only really need to set up one. And then we validate the transaction with that function I showed earlier. So this is the basic flow of creating a proof from a Bitcoin transaction. The user provides the transactions that they want to prove. They provide the UTXOs that are in the Bitcoin state to Shinigami. Shinigami runs the Bitcoin transactions through something called the Cairo VM, which allows you to get a trace of the program's execution. And with that trace, you can pass it to a prover. Our prover that we hope to be using in the future is called Stu, which allows you to compress the transactions trace. You can think about it as compressing the transactions trace into a Stark proof that is super efficient to be verified. So the prover provides this proof to you, and then you can pass the proof to any verifier anywhere. So it could be on Bitcoin if we have a Bitcoin Stark verifier. It could be on Ethereum, Starknet. It could even be like on your phone or something. You just run the proof, which is a much more succinct, short calculation than running all of the transactions on your own. And if you were vigilant, you might have noticed that I passed this UTXO as an input from the user for the Shinigami engine. And I could have just put anything here. So anybody could have just put an arbitrary UTXO that doesn't actually exist in the state, and then created a proof that that transaction was valid even though it technically wouldn't have been, because the UTXO doesn't exist on Bitcoin. So how do we track that users provide valid UTXOs? And that's where Shinigami consensus kind of comes in. So we have the separate library called Rido that does Shinigami consensus management, which includes the state management. So that would be where you store all the UTXOs that are considered to be valid. And you we use something called uTreeXO. The best way to think about it is you can think of it as like a giant Merkle tree containing all of the UTXOs that are valid. And then anytime you want to spend a UTXO, you provide a Merkle proof of the UTXOs that you spend, and then you recursively verify, or you also have to recursively verify that the UTXOs are valid previously from, sorry.
So I'm familiar with UTXO, which is pretty cool, but are you using that because these Stark proofs are, like, they don't like big memory things? Because the whole UTXO set is 10 gigabytes. The UTXO, sorry, just so we can get that. Oh, I was saying I'm familiar with UTXO. It really compresses the whole UTXO set in a few kilobytes. Are you using it because you don't want to deal with 10 gigabyte things inside your Stark proofs, or is it useful for some other mathematical reason?
That's exactly right. So we want to provide as little, or we want the Stark proof to have as little memory as possible, because the more large the amount of memory that we need is, the larger the trace and the larger the amount of time needed to prove. So yeah, you're exactly right. That's why. Shinigami consensus also does things that you might have heard from a previous project called ZeroSync, where it does difficulty checks, ensuring that Coinbase transactions are valid, and things like that. So you can ensure that the Bitcoin consensus rules are followed properly through a Stark proof. And this is kind of like an image of how that works. So essentially what you do to validate blocks in through, you see my cursor? Okay. To verify blocks in through M, or to prove blocks in through M, is you provide a proof of the entire Bitcoin state up to n-1. And this is kind of like induction, if you're familiar with that from math class. But essentially you verify that the proof from 0 to n-1 is valid. And if you do that, then you ensure that you have the correct chain state. And using uTreeXO proofs and the block data from N to M, you can provide that to the Shinigami consensus library and then create a new proof of from 0 to M, up to M. And then you'll just continually do this every time you want to create a new section or a new proof to post to a bridge or whatever use case you're using, which is what I'll go into now. So how much time do I have? So the essential idea of Shinigami, some of the use cases for Shinigami include initial block downloads. So when you start a Bitcoin full node, you have to essentially run all the Bitcoin transactions from Genesis up to the current state. Otherwise, you don't really know for sure if the state that you were passed by the network is valid. And with a proof, if you create a proof like this of blocks 0 all the way up to the current head, you can verify that proof. You'll know that all the consensus rules were followed, all the execution rules were followed, and that the latest state does in fact correspond with what is on Bitcoin mainnet. So you could do super fast and secure initial block downloads, start up your full nodes. We don't really have an estimate of how long it would take, but it would be polylogarithmically faster in theory. You could also do things like ZK clients nested in chains to do things like bridging. So this is kind of like a diagram explaining that. You get the same Stark proof proving the entire state of the Bitcoin chain. You pass it to an on-chain Stark verifier, and then the L2, L1, or whatever other protocol you're using verifies the proof. They'll know that the latest state is valid, and they can update the bridge's state so people can interact with the Bitcoin on the other layers. These two use cases were without OPCAT or any changes to Bitcoin Core. I also wanted to put a couple use cases that I think would be interesting if we had things like OPCAT, optimistic Stark verifiers, or like if you were just doing it on a separate network that had the ability to create Stark verifiers. And those are Bitcoin-like rollups and something that I'm calling Bitcoin threads. It's also been termed ZK threads by some people at the Starkware team. Essentially, the Bitcoin-like rollups is just like how EVM rollups work in a way. If you're familiar, you essentially just replicate how Bitcoin works in your own layer 2 or your own chain, and then you prove that chain state, and you can post the proofs to the Bitcoin. If you're using OPCAT or some optimistic Stark verifier, you could act like this other layer 1 in this image is just Bitcoin, and then you can update your bridge. And then the idea behind Bitcoin threads is very similar. You could imagine spinning off a Bitcoin UTXO that is set up with a Stark verifier, and you could run as much arbitrary computation or Bitcoin-like computation off-chain, and then whenever you're ready to post back to Bitcoin and you're ready to use the Bitcoin network again, you just post the proof to Bitcoin. The verifier verifies that the proof is valid, and then it updates the UTXO outputs with that. So it just kind of runs as its own thread in a way, separate from the network. And yeah, so the project's fully open source. We actually pay people that do contributions. So if you're interested in the project or you want to contribute or just like look around, this is a link to the GitHub. And if I have time, I can go into the code.
You got like 5 minutes for questions.
Yeah, that's good too.
Questions, comments. Where'd you come up with the name Shinigami?
Sorry?
Where does the name Shinigami come from?
So most of our exploration team projects are like named after anime characters. So yeah, it's from Death Note. It's the god of death in Death Note, yeah.
I'll let you guys pass it on.
This might be a dumb question, but you know, I'm not as technically inclined, but let me just lay it out. Like the mid 90s, you had Sun Microsystem and what that did for the internet. What I'm trying to understand is like what you guys are providing, what customer pain are you solving? How many other people, what are the alternatives that people could use instead of Starkware? And how do you monetize? Is it, or is it just open source and all that? Obviously, I'm asking from an investor perspective here.
So the project itself is not really set up to be used by or to make money, I should say. It's more of like a public good project. It could be used by things that are more money focused. Like for instance, I think the biggest thing that we want it for at Starkware is the Bitcoin bridge. So we want to be able to bridge from Bitcoin to Starknet. And to do that, we have to be able to verify that Bitcoin state is valid on Starknet. So if we are able to create the proofs using Shinigami, we can do that. I hope that answered your question.
Thank you. So I guess kind of follow up on that. Earlier you had the Shinigami consensus. Is there any kind of, looking at it again from like an investor perspective, using that as some kind of way to like validate UTXOs and kind of using that in some way, or do you envision bringing all of these together? Kind of. I guess the question is the origins of Shinigami consensus, and then where you guys want to take that.
So I think maybe also following or continuing what he was asking as well. So Shinigami consensus, mainly the main origin is from something that ZeroSync was doing. They were doing it to build these Stark proofs for bridging and just like use cases around that field. But also, Shinigami consensus can be used to do what I was discussing, like the rollups. So you can imagine a lot of Bitcoiners, they like the idea of Bitcoin. They want their money to be just used through Bitcoin's spec, only for spending, not really doing things like AMMs or NFTs or anything like that. So you can imagine if like you're an investor creating some kind of roll-up that's like Bitcoin, and you could pitch that to more Bitcoin maxi people, or like just people that are more interested in how Bitcoin works and only doing transactions. And you'll be able to process a lot faster and still be decentralized without relying on like optimistic rollups and things like that. You could just create proofs of a giant chain and yeah, if that makes sense.
So just to confirm, with Shinigami, we're not restricted to Bitcoin-like functionality inside the rollup itself.
Did you say that again? Sorry.
So we have obviously Bitcoin script. You're not restricted to primitives or scripts that you could create in that. You're able to do a roll-up of anything in a more Rust-like manner.
It would still be a roll-up of Bitcoin script execution. So it would be just like Bitcoin. You wouldn't be able to do like Rust programs, for instance, if that's what you were saying. But technically you could extend Bitcoin's functionality through Shinigami and it would still be provable. Like for instance, if you wanted to activate opcat on your own Bitcoin rollup, you could still do that with Shinigami. I mean, not currently, but it's possible to do it with Shinigami, and you'd be able to create those Stark proofs in the same way. Does that make sense? Yeah.
Yeah, I appreciate that.
Yes, so my understanding, if you want to do some, computation on blockchains is very expensive. If you want to go do it somewhere cheaper and create a proof and then just put that proof on chain, that's a lot cheaper to do. But my question is, what is the feasibility for an average user to be creating proofs? Because those are pretty computationally intensive. So even though you're doing it in a cheaper environment, like what does the cost look like if I'm a user and I want to create proofs of Bitcoin-like execution to post on chain?
Yeah. So in the current state, creating proofs is not very friendly for end users. Like, I'll give an example. So StarkNet itself has its own prover, and Starkware runs the prover, and it is very large. I don't know the exact specs, but I imagine it's somewhere around like 500 gigabytes of RAM, which no user, I don't imagine anybody in this room has that much on their computer. He does back there. But with the development, we're developing something called Stew now, which is, we don't know the numbers exactly because it's still in development, but we expect it to be a lot more friendly for end users to be able to do what we call client-side proving, where you can create proofs on your phone or on your laptop. Creating proofs of Shinigami execution in particular, though, with Stew, I'm personally doubtful that it will still be friendly for end users, just because Bitcoin transactions are so large, the transaction execution context can be massive. So yeah, it's the good thing about provers, though, or like creating Stark proofs, is that only one person needs to run the prover. One person creates the proof, and once it's done, anybody can verify it, and it's very, very efficient to be verified. That's the purpose of it. So while it would be really good to have proving be commercially available or like be available to end users, it's not a deal breaker for most use cases at the current moment. Yeah.
Thank you.
Hey, thanks, Brandon.
Yeah, thank you.